Hi, and welcome back to our discussion of geologic structures. These are features that are the result of tectonic processes, shear stress, normal stress or compressive stress, and tension. What you see here first, we're going to talk about our joints, and we'll move into talk about the different types and classification of various fault systems. In this case, what you see here are a bunch of lines in this sort of craggy rocks, and these are cracks. They haven't been displaced or shifted, so the right side over here hasn't been shifted up or back relative to the left side. It's just a split, and you can see they're very regular in their orientation and in their sort of pattern, and we call these joints. Now, normally they're not that well organized, but in this case, I picked an example that was, really linear. If, for instance, one side of the block here or on the other side over here on the right hand side had shifted, that would be then called a fault. Okay? A fault is a crack across which a block has been moved or shifted. You can see here we have a layer here that continues down here, so this layer has been shifted down relative to this which has been shifted up. Okay? Faults have two sides. Each block has a name. The upper block is called the hanging wall. Okay? Hanging wall is where you put your head or your tools. And the right-hand side here, the block below the fault, is called the footwall. Okay? And if we can identify the hanging wall versus the footwall, then we can really determine the kind of fault. We can define the kind of fault that's present. So footwall is where your feet go, hanging wall is where your head goes. And so if I was to draw a little diagram and said, oh, here's a layer that's been split just like this. We'll color that in red, color this side in red, right? The layer used to be continuous. And I said, well, which is the hanging, which is the foot? So here's A, and here's B over here, which is hanging, which is foot. Draw a little stick figure. Feet go in the footwall, so B in this case is the footwall. Head in the hanging wall, and so A is the hanging wall. Now, let's take a look at the kinds of faults that we can get. In this case, on the top left-hand side, we have what's called a normal fault. Okay? In the case of the normal fault, we have the hanging wall has moved down, footwall has moved up. Okay? Hanging wall down, footwall up. You can see the bed cutting across, and that indicates that it is a normal fault. That's by definition a normal fault. The fault is forming under tension, so we're pulling the crust apart. That's the kind of force that's involved. And over time, this segment of the fault, this little part right here that sticks up, which is called the fault scarp, the scarp is going to erode away. Okay? And as the scarp erodes away, we flatten out the rocks. Okay? We flatten out the surface, I should say. And that means that we expose different rocks. So in this case, across a normal fault, I'm going to say something about the age of the rocks. The rocks in the hanging wall are young, and the rocks in the footwall are old, right? This layer, this brown layer here, which is offset, is older than this light brown layer. Okay? Light brown layer used to be here, but has been removed. So we have old here, and the younger layer exposed on top. Now these faults commonly come in groups, and when we have groups of faults, both normal, here's a normal fault and here's a normal fault, the downdrop block here under tension is called a graben, and this is a horst. We reverse the dip of the faults, so here we have a graben, here we have a graben, and then horst in the center, right? The horst becomes mountains in the crust, and then the graben becomes a valley. So this is for a normal fault. Here's a sketch of a small normal fault. You'll see the road bed down here at the bottom, right there. So this isn't a very big fault. Here's the one fault, two faults. There's another third fault right there. and you can see the layer has been displaced there, across there. This one's really been dropped down. Okay, this is the hanging wall. This is the foot wall. Hanging wall down, foot wall up. By definition, that's a normal fault. Okay, hanging wall down, foot wall up is a normal fault. In this case, the Horst is in the middle. Graben is off to the side, or off to the side over here. If we change the kind of stress we apply to the crust, and we change that stress to compression, we're going to push the rocks together, arrows coming together parallel to each other, facing in opposite directions. This case, the hanging wall is up, the foot wall block is down. Hanging wall up, foot wall block is down. That's a reverse fault. Okay? Now, if we erode the surface right through here, we cut through it, just like we're going to come down to this block diagram. We see the old rocks in the hanging and the young rocks in the foot. By definition, we see the old rocks in the hanging and the young rocks in the foot. So that means if you just had a map and you said, oh, there's a fault here, and I know that this is the hanging wall and this is the foot wall, you know the ages here of the rocks. You don't have to see the relative motion of the blocks. You can interpret it based on the age. Okay? There's a special kind of reverse fault, still forms under compression. It is called a thrust fault. Notice the angle I've drawn down here at the bottom. This angle is less than 45 degrees. When the dip of the fault plane is less than 45 degrees, we're going to call it a thrust fault. Here's an example that you might take a crack at drawing in sketching on a piece of paper. Might go ahead and pause and just give it a shot. See if you can identify the fault. I would try to draw in like this black marker layer and then see where the fault might cut through it and where you sketch that in. Okay, so you've hopefully given it a shot. I'm going to just show you how I do it. So here's the marker bed right here. It cuts all the way over like that. This one cuts up like this, cuts up like that. Now, this is all erosional stuff in the middle here, so it's covered up the white rock, but the fault sits right there. Okay, and what we can see is that this is the hanging, H for hanging, and the foot wall is here. If I drew my stick figure, right, feet in the foot, head in the hanging, motion like this, hanging wall down, foot wall up, that is a normal fault. Normal fault. No Graben to look at in this diagram. Take a look at this one. Let's work on it and see if we can figure it out. Take out your piece of paper again, or a scrap paper in your notebook, and see if you can sketch this out. Might be helpful. All right, so let's identify the fault first. Here it is. I'm drawing it in. Broken or ruptured layers. You can see here this layer or set of layers here is continuous with this layer up top. Okay, let's identify the hanging and the foot. Well, let's draw our man crossing the fault. Head is in the hanging wall. Feet are in the foot wall. Okay, so foot on the left, hanging on the right. In this case, it's hanging wall up, right, relative to foot wall, hanging wall up relative to foot wall. And so this fault then is a reverse. This is terrible. You're going to let me erase. It's a reverse. All right. One last type of fault to talk about. So a normal fault is forming under tension, a reverse or a thrust fault is forming under compression, and then we have faults that form under shearing. And these are called strike-slip faults. And they're pretty easy to identify. The fault planes themselves, so I'll draw it in here, tend to be vertical. Okay, so they typically don't have very much dip at all. And you can see the fault plane is right there. In this case, we're looking at features on the Earth's surface. So this is a stream I'm tracing in on the left-hand side block. Oops, daisies. It's back it. It's getting a little wild there. This is a stream I'm tracing in on the left-hand side. You can see it here. So we're looking at the Earth's surface. And there are two kinds of strike slip faults. There are left lateral and right lateral. Again, all we're trying to do is determine the relative motion of the blocks on each side of the fault. So if I stand on the fault, or sorry, I stand on a block, and I look across to the other side, I want to look and see which direction the other block has moved relative to me. So I look at this stream, right? The stream has moved to the right relative to this segment down here. So that's a right lateral, okay? Right lateral. If I stand on the other side, you're maybe asking the question, does it work the same way? I gotta stand on the other side, so I can pick any block, I look across, right? This segment here used to be connected to where I am over here, to this segment, and it's shifted to the right. So it's still an example of a right lateral fault. This is a famous one. You can see the fault here. This is the San Andreas. And the question we'll ask is, one, is it right or left lateral? Let's take a look at where the fault is. I'll draw it in right here. You can see it. It's this little divot. It's really easy to see because it's getting eroded a little bit more than the other rocks right there. You can see the drainage comes down, hits the fault, and then takes a bend and then continues on down like this. Right? So if you're standing here down at the bottom on this stream, relative to you, this stream has been shifted to the right. So this again becomes a right lateral strike slip fault. All right, let's talk a little bit about plate tectonics and different kinds of faults. Okay? Faults commonly form in groups. They rarely form by themselves. And so if we have a kind of boundary in which the crust is being pulled apart, the deformation style there, the stresses there, are extensional. And so when the crust is undergoing extension, we would expect, right, normal faults to form. This is happening in the basin and range. You can see in this picture here, here, and here, those are all grabens, or sorry, those are all horsts, right? Upthrown blocks, part of the normal systems. This is a playa lake or a valley. That's the graben. Graben and graben. If we go and look at Everest, which is here, okay, in the bottom left, that's part of a contractional style deformation. So those rocks are under compression. Compression creates reverse and thrust faults and thickens the crust. So we would expect a convergent boundary. So divergent boundary for normal faults, convergent boundary for reverse or thrust faults. This is a gross generalization, but it mainly works. Then the last thing to look at is the strike slip fault. Now, just shearing across a strike slip system doesn't create mountains. What you need is something called a restraining bend and a releasing bend. And so here's the fault, and a restraining bend happens when the fault curves and makes a jog, and then curves and makes a jog. This particular fault is right lateral, so the block moves this way on the top and the block on the bottom moves to the left. Right? So I stand on this side, look across, it's shifted to the right, that's right lateral. Now in this area here, though, the forces are not shearing, they become more compressional. And when you have compression, you get mountains stacked up, thrust faults, reverse faults, that kind of stuff. And so the San Gabriel Mountains have been popped up in this, what we call a restraining bend of a strike slip fault, where the forces in the fault are tensional because the bend flips the other direction. You end up with a releasing bend. You'll get lots of normal faults, Horst and Grabens, sag ponds, and those kinds of structures. Pull apart basin is sometimes also what it's called, associated with a normal, or sorry, associated with the strike slip fault. Okay? All of these faults are part of a set of events that are spatially and temporally related. Okay? They are part of what we call orogeny. Orogeny consists of many different things we've already talked about in this class: folding, faulting, magmatism, metamorphism. All of those can be going on during an orogeny. And we know that, in South America, we have an orogenic event going on right now. We have mountains, we have volcanoes, right? All of that is orogeny. What mountain systems do we have in the U.S. that we know of? Okay. How about the Appalachian Mountains? They're located on the east coast, or the east side of the U.S. They have metamorphism, folding, faulting, somewhere between 450 and 300 million years ago. They're part of the Alleghanian or Appalachian orogeny. We have the Rocky Mountains, again, folding, faulting, magmatism, not hundreds of millions of years. They're called part of the Laramide orogeny at about 60 million, 65 million years ago. Okay? Some of the mountains in the Sierras are part of the Antler and Sevier orogenies. Those would have been occurring more like 120, okay? 100 or even 80 million years ago. And those would have been part of, let's say, the Sevier orogeny. And then the Antler orogeny would have been much older, actually, and the arc from that is still hasn't been kind of located. The magmatic rocks related to it haven't been found. Okay, so we have the Laramide, which corresponds to the Rockies. The Appalachians, right, are the sort of Alleghanian Appalachian orogenic event. The Sierra Nevadas are part of an orogenic event, and then any modern volcanoes, we don't talk about it, but in the Pacific Northwest, those are part of an orogenic event where you have deformation, metamorphism, magnetism, faulting, and folding. Spatial location and temporal span as well. All right, so that wraps up my discussion of faults. Things to consider: normal fault, right? Relative motion of hanging wall versus footwall. In a normal fault, it's footwall down, hanging wall up. For reverse, it's hanging wall up, footwall down. And for strike slip, you don't care about hanging wall and footwall. You want to know if it's right lateral or if objects have been shifted to your right if you look across the block, or left lateral. All right, that'll do it for faults and orogenies in this segment.